Nous avons le plaisir d'accueillir Philippe Lanane, que vous connaissez, je pense, hein, qui travaille donc à l'Institut d'optique, au laboratoire de photonique à Bordeaux, et qui va nous présenter aujourd'hui une série de codes, dont Reticolo, avec quelques-unes de ses ramifications. Et je crois que Philippe, tu avais aussi prévu un peu de discuter justement de l'élaboration des codes libres et de leur diffusion, etc., et de tout ce qui entoure tout ce travail, il me semble.
Ouais, c'était ce que j'avais planifié au début. Je n'ai pas trop
Ah,
insisté en le préparant,
d'accord.
mais je
Ok.
suis vraiment prêt
Si,
à en discuter en fait. Je trouverais
si
que ce
tu veux
serait intéressant.
voilà, si tu veux nous partager ton expérience, ça sera avec beaucoup de plaisir. Bon, eh bien, écoute, on va démarrer cette séance. La parole est à toi, Philippe.
Okay. I will speak in English. So thank you, Emmanuel, and thank you for GT1 of GDR On for organizing this Tour de France of, let's say, software, electromagnetic and acoustic software, as far as I understand. Um, I will. Alors, doesn't work. Uh, okay, sorry. Yeah, now it works. Maybe. Yes. Yeah, basically, I'm going to speak about four codes which have been developed at Institut Optique since something like 20 years or even a little bit more. I would like to thank my collaborator in Bordeaux, Tang Wu, and in Paris, Jean-Paul Hugonin, who is following my talk with Christophe Sauvant. I would say that all code are written in MATLAB, and one way to access them is to go through the web page of my group, and then you will have a link to Zenodo and normally the latest version. So I'm going to start by what is called reticolo grating, which is a code which is based on the rigorous coupled wave analysis. It's a code, of course, which is maintained. If not, I will not talk about that. The first version has been launched in 2000, and it has been initially sold to industry from 2000 to 2011 with a very good documentation and reliability. I would say at that time, people, let's say in the field, doesn't have in mind to have a freeware. Something like a personal code was like a treasure, and so you keep it or maybe you sell it. Uh, then it was transformed in a freeware package when S4 was developed in 2012. I would like to say that it is a code which is a result of extensive research. We have published on the method RCWA itself, something like 10 journal articles. It's also currently gaining increasing attention. I don't know really why. Maybe due to the growing research activity on metasurfaces. I would like to say that this code has been designed initially for designing metasurfaces. It's also widely used by industry. Maybe this is not well known, and we know that because from time to time we are receiving an email from companies, and I am going to
Et
one
qui
show,
dépend de quatre arguments.
and I am going to show one example later on. A specific feature, there are many rigorous coupled wave analysis code in the world. Maybe specific feature of this code is include a block mode computation, an accurate computation of the loss per layer, a use of symmetry for speeding up computation, and that can be a considerable speeding up, everyone knows that, and especially in 3D. Jones matrix computation, and I would say a special unpublished S-matrix scheme. I don't know if this scheme is known nowadays. Let's just mention something which is extracted from an email that has been sent to Thomas Krauss with me in copy, where the author say a big part of that work is finding and benchmarking different simulators. We found that compared to S4 and other lesser known simulators, Reticolo RCW is both faster and more accurate. A more detailed look at Reticolo indicate that it is able to set up the eigenvalue problem faster or something like this. This is one author opinion, but I just mentioned it. It's an expert in numerical modeling, by the way. I just mentioned it but it is just an author opinion. Of course, we cannot conclude this. Here I have finished with reticular grating, right? And I would like to now try to speak about extension of this reticular grating and introducing that by an email. Jean-Paul and myself received something like 2 months ago here, and coming from Sony. We were not aware that Sony were using Reticolo from that time. And look at the title only, request for permission to use Reticolo V9 and Reticolo complete version. So request to use Reticolo V9 because the licensing that we provide in Reticolo is so bad that maybe people in industry hesitate to use it, but it is a freeware, so everyone can use it. But we were more interested by Reticolo complete version. What does it meant by Sony by that? We don't know. But what I can say is that in our intern terminology, it refers to an extensive collection of MATLAB code developed essentially, or no, most developed by Jean-Paul over more than 20 years. It is not possible for me to provide an overview of this code. I mean, I will not be capable. But I would like to highlight a few extensions of this grating code that we have provided, and that I think are worth to be known. The first extension is about the Fresnel coefficient computation. Let me Fresnel coefficient at the interface of periodic media. So those coefficients are analytical and well known when you have an interface between two uniform media. And of course, you use plane wave expansion, and then you have the Fresnel coefficient. Of course, you can generalize that when you have let's say here a uniform media and here a periodic media. And then you can match the boundary condition at the interface between plane wave on the top and block mode expansion in the bottom, and access to all those reflections from block mode to block mode, or to plane wave, or transfer function from plane wave to block modes. You can also do it for an interface between two periodic media. That's a general knowledge of how electromagnetic energy exchange at an interface. And I would like to say that Reticolo, not the grating one, not the one available on the web, but the in-house extension can provide that, and we will be glad to collaborate in order to that. An example, we have spent a lot of our career to compute modes, various kind of modes, and here I would like to say how we can use this extension here to compute the surface mode at an interface between here a uniform medium, which is air, and a substrate, which is metallic, perforated by holes like this. And here what you see is that we compute the surface mode at this interface, which was called at that time a spoof plasma, where you see here we have the complex frequency, which is plotted here for that mode as a function of the real value of the k-parallel vector. So we find two usual modes here. This also, the fact that we are analytical in terms of block modes allow us to, let's say, have an effective computation for many thickness. Here you see in this code, I mean, the thickness is introduced as a line space with 1,000 elements. And in fact, what is implemented is because we have the interface matrix, the exchange of energy, we implement something like a Fabry-Perot propagation into a grating layer, for instance. I would not say that it is as efficient to compute 1,000 thickness as one, but the increase in price is really ridiculous. This is what I can say. It's basically comparable to the price you have to pay to compute the eigenmode of one layer. I would like to speak about another extension that we named at that time in 2000 when we imagined that the aperiodic Fourier-Motal method, or the aperiodic rigorous coupled wave analysis. A way to mention that nowadays could be a supercell method with PML. We have provided a lot of extensive work on that over something like almost 10 years, as you can see here. And the idea is to apply it here for integrated optics. So you have an initial open problem where you see you have the guided modes like this, which propagate and can scatter in an open space alone and below. This is a substrate and this is the upper strate. And what we do is we do an artificial periodization right? You see like this, where in the periodization we have a supercell and we introduce, let's say, absorbing boundary of perfectly matched layer in between. Here I would like just to mention how it was easy. I remember that I performed this generalization from a grating code to a waveguide code. Is something like one afternoon. Let's say in 1D. So you have two ways. You take the rigorous couple wave analysis and Monder shows the eigenvalue formulation. Then you have two ways to implement that. Either you can, let's say, implement a coordinate transform, which will be, let's say, a PML or whatever. So simply you transform the derivative operator Kx that you have in the rigorous couple wave analysis into the product of a Toeplitz matrix multiplied by Kx. Or you can, you can also implement perfectly matched layer by modifying the epsilon and the mu of the layer, which means in that case you simply modify the E matrix, the E Toeplitz matrix and the A Toeplitz matrix. It's actually very easy, and then you can use a scattering and S matrix scheme, to propagate. So it's obvious to do. Here I would like to mention an old benchmark that we provided on the method a long time ago. I would like to say that benchmarks are very important in my opinion. They challenge your method and your implementation. They also make your better understanding its limitation, and also they make you aware of limitation of other methods. And I am really surprised that nowadays, there are less and less benchmark articles. And also I am surprised that people publish more and more their code without really benchmarking their code by contacting other people. In this article where you see you have something like 20 authors, we benchmark 3 aperiodic Fourier modal method implemented by different people in different groups, 3 FDTD, the method offline, the exact modal method, FEM, volume integral method, etc., etc. And for this 2D problem, was chosen a 2D problem to be simple so that many people can participate. Then you have a groove, which is, let's say, and a slit, which are illuminated by a plane wave. But what's happened here is that the groove, you see, is going to diffract light, and some of the light is going to propagate on the surface to reach the slit and interfere with the direct light. So that means that as a function of the slit groove distance here, the transmission has an oscillatory behavior. And you see, we have been able, even for large separation distance here, we have been able to perfectly superimpose 2 implementation completely different of the aperiodic Fourier modal method. In one implementation here in black, you see we have a supercell periodization into the transverse direction, whereas here we have a supercell method implemented into the longitudinal directions. And the 2 methods are completely different. Also, they both rely on the square, and they provide very, very nice result. You see, this is the best FDTD result, which is outperformed. I finish by giving this example here, where the kind of computation, so that's what is called the nanobeam cavity nowadays. I would call that in the time where we were working a Fabry-Perot cavity in a ridge waveguide, where you see you have 2 Bragg mirror, and here you have the Fabry-Perot, let's say, mode, which is bouncing back and forth in between these 2 mirrors in the waveguide. What is used here is the aperiodic Fourier modal method. So we periodize in X and periodize in Y and solve in Z the problem with the S matrix method. And here is the result of the computation, where what I just want to say, we wanted to reveal some phenomena that is not worth to be discussed here. The fact that here you see we have for this Fabry-Perot resonance a very high Q. But the calculation which is provided here, even to display it, it was difficult. There are many H value and many wavelengths value. I think that if you want to perform this with COMSOL nowadays, you have 6 months of calculation, whereas in that case, probably at that time it will represent something like 1 week. And this is the force of the analyticity when you integrate Maxwell equation. That's no more than that. Just one side on a very specific software that we call the RETOP, which is a near to far field transformation. So again, it's the same as before. You can find many near to far field transformation are known since, I don't know, maybe the 1960s or something like this. There are a lot implemented for antenna. If we publish this, is because we provided some originality into the implementation. And the originality is the following one. In that case, you imagine that you have a scatterer and a source, whatever, a finite size resonator onto a substrate, right? With, let's say, several layers, for instance. So you can have, when you illuminate it, you can excite guided waves. And so what we have implemented into this software is a radiation diagram into the guided wave. I mean, the guided wave can be launched into all direction into the planar waveguide. So that was the originality, and this is why we publish it. I would like also to say that COMSOL, for instance, incorporated last year in his official application gallery, not the guided wave implementation, but the free space radiation diagram. Because before in COMSOL, you were able to compute the far field only in a homogeneous medium, in a uniform medium, not for case where you have substrates. Then I'd like to talk about the last, let's say, version, which is what we call a Reticolo film stack, which is entirely provided by Jean-Paul. I have not contributed to that, which is for the analysis of stack of anisotropic uniform layers using the 4x4 matrix multiplication. I would like to say that you can find many codes, many freeware about that. So we don't have any publication on that, just we have a release in 2024. I am using this code in Bordeaux quite often. I mean, I would like to say that I find it very fast because of the vectorial computation which is provided. You can compute many wavelengths and many thicknesses at the same time. It's very stable. You have many examples. I remember the perfectly lens, for instance, by John Pendry, which is implemented. And just would like to emphasize a little bit the fact that it can also compute the guided mode of the stack, either by using complex K value or complex omega value. This is the case here of a computation that I performed, let's say, in New York last year for hyperbolic surface polariton mode, where you see here the line which show you the imaginary part of omega, whereas, and here is the location, so you have the hyperbolic dispersion on the surface at the interface between two material, one being air. I would like also just to mention that this surface mode calculation, I mean, which has been popularized by very nice article published in Nature. I mean, in my opinion, and also I discussed that with Jean-Paul, I mean, something like a mistake in the literature. The mistake that when they introduce loss in their calculation, I mean, those crystals are in general absorbent. In fact, they see the problem as something like 6 almost independent variables, which are the imaginary and real part of the kx and the frequency. Whereas, in fact, you have only 3 independent variables which are complex. That's a little bit. And so they have introduced in the literature, this is taken from a review article. And also you can find that in a supplementary material of this article. They have developed a novel procedure, they say, based on the minimization of the loss for each direction of K prime. And I believe this is not correct what is done here. Just to say that this is not always obvious, or it can be debated at least, to compute a surface mode, even nowadays, at the interface between two media. I will now move to the presentation of the software MAN, which is called the Modal Analysis of Nanoresonator. I'd like to say first that this software is a result of 10 years of research. We have published something like more than 30 theoretical papers on the mode of nanoresonator. If you go to the website of my group, then you will see that we have a user guide video. I will provide an extract just after. And we have also an introduction video where basically we explain what is a quasi-normal mode and how you can use them efficiently to understand the physics of nanoresonators. I would say that this mode of resonator, I mean, there are solutions of Maxwell equation without sources. Because, I mean, in general, you have a finite system, you have leakage and absorption. If you have, for instance, a plasmonic system. So that means that the Maxwell operator is not self-adjoint. The eigenvalue that you find are complex, complex frequency here. In quantum mechanics, they talk about complex energy, sorry. And the eigenvector are called quasi-normal mode. They are in general neither complete nor orthogonal. There have been a lot of work in different disciplines, including mathematics, about quasi-normal mode, completeness, and orthogonality. So in a quick presentation about the software man, I would say that first what we have done is we have developed two solvers to compute and normalize the quasi-normal mode. I would say that many software, actually, like COMSOL, compute the quasi-normal mode, but don't normalize them. They don't always compute them well, but anyhow, many software, ANSYS for antenna business, COMSOL can compute them. So what we do here with these two software, the first one with this QNM Pole, which has been published in 2013 when we first realized how to normalize quasi-normal mode, and the second one in QNM Egg, which is this one back to COMSOL. And so what those software help you is if you have your own software to solve Maxwell equation, it helps you to compute the quasi-normal mode and to normalize them. I would say that both solvers apply to, I would say, virtually any material, including non-reciprocal material and any geometry. I use the word virtually, right? Because, of course, it's very easy to find some geometry that cannot be computed. Here is an extract from Tong user guide video where he explained how to use this solver egg.
De notre côté, Philippe, on n'entend pas le son de la vidéo.
I am sorry about that. So he's explaining how to play the game between QNM egg and QNM pole. And now I will show the result of the, sorry about that, about the modal analysis. I mean, the result that you have. So now you have calculated you have launched a model and you have computed the mode, and we display first the complex plane where you see you have the imaginary part of omega and here the real part of omega. So each point here is actually a mode which has been calculated. We have made a lot of effort to sort the mode, I would say, and here you see that the color that we print here give you the probability that the mode is actually a QNM and not a PML mode. So you see there for the green value here, you see it's obviously a PML mode. The resonator is there. So you have a, a surface mode, basically, mostly on the boundary between the PML and I don't know, the air or the region, the physical region, which is there. And the other way that we have also that we provide here the probability that the mode be efficiently excited by a plane wave, for instance, and that's the size of the dot here. So you see that for that mode here, which is yellow, so it's QNM, and which has a big side, it's the dominant quasi-normal mode. It's a mode which will be the most excited in your system. Once you have the complex plane, in fact, you have a lot of information. For each mode, we provide the quality factor. And soon you will see, I will explain you that we are going also to provide the Fano factor, the Q Fano factor. And also because we have the mode field, in fact, we have access to the mode volume here, which is the inverse of the square, basically, of the square of the electric field. You can have also a magnetic mode volume. Once I am talking about, of course, a normalized electric field here. Then once we use this solver to compute the quasi-normal mode, then we offer a number of toolbox, which are, let's say, increasing over time. Each time we work on quasi-normal mode theory and apply it, we develop basically a new toolbox. Here is a small list of the toolbox. And when you go to the toolboxes, in fact, what's happened there is that for each toolbox folder, it's composed of a user guide, document, and also several dedicated examples. Here are COMSOL model, where basically you can find a bow tie. You can find a nanocube here on a metal particle, what's called on a metal substrate, which is called an NPOM. You can find also silicon wires, which is interesting because the dispersion of silicon is not easy to handle. And we try to handle let's say, efficiently and accurately. So this is a QNM reconstruction toolbox. You have also temporal toolbox, nonlinear toolbox, etc., etc. Alors. Just example what you can do with this mode volume that I was discussing before. I think it's an important concept. Here at the case, what you can apply is first order perturbation theory that give you the frequency change and the Q factor change also, which is due to the fact that you can perturb locally at any position by a small polarizability alpha. So you see it's this change in frequency, complex frequency, is simply inversely proportional to the mode volume. So once you have calculated the mode, normalize it, you plot 1 over E square, and you know directly where you can put and which will be, you know, analytically, what will be the change. Recently, this has been used by Massimo Gurielli in Lens, in Florence, to, let's say, optimize the quality factor of photonic crystal cavity, because you can know by this formula what's happened if you increase a little bit the size or decrease it, the size of the hole, or if you shift it a little bit. And if you compare that to what has been done in the past with a lot of calculation, I think it can be a great advantages. Also for the Purcell factor, there is another example you see published in 2013, so it's not new, where basically you have here a gold dimer, right, where you have dominantly two modes which exist in that system. And again, you compute the modes with the solver, you normalize them, you go to the mode volume, and then after that, you have an analytical expression giving you the Purcell factor. In fact, the total modification of the spontaneous emission rate and an emitter as a function of the sum of the Purcell factor of each mode here. So here you see that for this system, we have two dominant quasi-normal modes, that the mode volume, when you place the emitter in between in the gap here, is given by this number. You plug into this expression, then you have the blue curve as a function of the frequency of the wavelengths, the green curve, which correspond to each mode. You make the sum, you have the red curve, and then you can compare to a COMSOL calculation of the total modification of the spontaneous emission rate. You have a small discrepancy because, I mean, of course, you have other modes than these two dominant modes which participate, which are also excited. I would like to say again, the strength is the analyticity of the method, both as a function of the position of the source and as a function of the wavelengths here. So temporal analysis toolbox here, where you see this is here the case of 3 metallic rods which have been analyzed. So you send a pulse on them and you compute the field at one position in the near field, right? And this is what you compute with the FDTD. And basically what you observe is a beating. With the modal analysis method, and you look at the mode of that system, you find 3 dominant modes which are there. The excitation coefficient, which depend on time now, is known analytically, right? And you can simply write that this beating is a sum of 3 contributions, this one plus that one, which is very recovering almost perfectly the FDTD calculations. What I would like to say that if you use, so what you understand is what is the origin of the beating, okay, by doing that. Another point is, imagine that with the FDTD, you want to change the polarization of the incident pulse. You want to change the pulse width or the direction of the plane wave, which is exciting, then you have to recompute all. With the modal analysis, the modes are already computed, and the beta are known now are going to be different, but they are known analytically, so it can be extremely fast. I would like just to mention, I mean, evolution. I mean, we are still working on that, still working on QNMs, and this is what we realize about the Q-Fano parameter, I mean, which has been discussed a lot in the literature since a long time. And in general, the Q parameter, the Q-Fano parameters is understood as an interference between a bound state and the continuum of state. And this interference, in fact, forms what is called the quasi-bound state. And the quasi-bound state is a quasi-normal mode, in fact. And recently, we realized, of course, the quasi-normal mode tell you, I mean, the mode which is confined and also the leakage and the absorption. So it's really the quasi-bound state that is computed. In that case, and recently we understood that we can have an exact analytical expression, in general it's fitted, of the Q Fano parameter. I am not writing it because it's a little bit long, but you can find in this archive paper. And so next, when we will publish that paper, I mean, we will have a toolbox, just an example, on Fano calculation, where everything will be given. The MATLAB code can be just read and can just be copied or modified, whatever you want. And also we are going to introduce into the Eigen solver where we display the complex plane. We are going to introduce this Fano parameter, which is already very important. Like to place man in a broad landscape, I will try to do that. I would say virtually all software COMSOL compute quasi-normal mode, not always perfectly, right? But don't use them to reconstruct. And in fact, this is due to the fact that mode normalization is difficult, that the theory is difficult. But once you have a quasi-normal mode normalization, then you have at your disposal a lot of very simple closed form expression for many physical parameters. I talk about Q, mode volume, Fano, Purcell expression, first order perturbation theory expression, which are all analytical. You can have coupled QNM theory also, and many other things like that. I would like also to say that for me, it's something like a new path in nanoresonator modeling, this quasi-normal mode expansion, because it's fast and accurate. Not always, but mostly. Analytical with respect to the frequency, and that's unique. It gives you transparent physics, that's unique, and this is why, in fact, we developed the method. I like to say that they are from our group, but you have also some other review article, but from our group, we have some review and perspective article, and also insight article. I mean, I would like to encourage you to look at this last paper, which is submitted. I mean, still, we can provide correction if you have a feedback, which is a reflection on the spatial exponential growth of electromagnetic quasi-normal mode. And at the end, we discuss how quasi-normal mode theory represents that. And you will see that if you read it, that's not so easy. Also, would like to highlight some point here that I am often doing, that about the quasi-normal mode normalization. There have been a mistake over many years, many decades in the literature, and it's not always easy to correct mistake. But in that paper, written by Sauvin and collaborator in 2002, in one of the sections, we provide a complete clarification of this normalization issue. I would like to say also that two other groups, at least I am aware of, are also developing similar freeware. At Institut Fresnel in Marseille, Guillaume Demézy and collaborator, and at Zeus Institute in Berlin, Sven Berger and collaborators. Finally, I would like to introduce current work. So this is not deployed, I mean, launched. I mean, it's not a freeware yet, but this is some work which has started, I don't know, in Palaiseau 10 years ago, and which that we are providing in collaboration with Kevin Vink, which is now no longer with us, where we try to develop a code for analyzing large-scale metasurfaces. So the basic idea, and there are many, it's well known, is to avoid to sample all the space like with FDTD. And what people want to do, I mean, for instance, in the T matrix, which is well known, I mean, they take time to learn how one meta-atom scatter light, and then they use the green tensor to implement the multiple scattering and solve the problem. So it's a very general approach. What we try to do in this global polarizability matrix is, in fact, we try to find a small set of what we call numerical dipoles. So they are dipoles, but they are numerical. I will explain why. So that when we know the polarizability matrix of this numerical dipole, it is capable of reproducing the near and far field, but the near field, you say, around scattered by any kind of wave in the near field of the particle. So what is this polarizability matrix? So the most important element of it is non-local. In fact, this non-locality introduces us degree of freedom into all those elements that we pre-compute. I would say this is the equivalent of the T matrix. It takes us time to optimize this element so that the scattering field by this particle looks like the scattering field by the numerical dipole. What do I mean by non-locality? Is that you see that the field which is, for instance, impinging onto the dipole R3 at position R3, I mean, that field directly polarized the dipole R1, for instance. So this is, you see, it's the off-diagonal term of this polarizability matrix. So here we have many degrees of freedom when this matrix is huge to optimize in order to match these two scattering problems with a small number, of course, of numerical dipoles. That's the idea. Let me show you an example. This is here where we compare a COMSOL here, right, with our implementation for, I don't know, silicon nanorod in air. And you see that we have 10 numerical dipoles. In fact, each dipole is 6 polarization for px, py, mu x, mu y. Okay, but it means that here we have only 60 degrees of freedom to represent the scattering by this particle. It means that the size here of this induced polarization is 60 only. So if you compare that, we are quite accurate as soon as we are outside the learning box here, which is shown here. It's comparable to COMSOL, absolutely, but only with 60 degrees of freedom. Just realize, in COMSOL, I don't know how many degrees of freedom of finite element we use to provide this result. Okay, but it's not 60. Here is a comparison with 16 cylinders, which are like this, something like that in that problem. Just I want to say that, I mean, compared to COMSOL, we have a huge reduction in RAM, which is necessary to perform this calculation. Extension, what is presently done in Bordeaux, is an extension of that we already provided, in fact, in the thesis of Maxime, but we continue to work actively on that. You have limitation with the T-matrix method. I mean, the limitation that you cannot have two particles that interpolate the circumscribing sphere that I show in blue. This is well known. With our method, I mean, we compute the field just in the near field. So as long as this near field doesn't touch, we can handle that. And also, I would like to say that we can also now, this is a development which is performed, we can handle the fact that the particle can be deposited on a substrate, can be even buried in the substrate, or can be at the interface between two different media. Yeah. Now, I would like to just to finish, I would like to move to, I don't know, maybe I still share my screen, right? Yes. I want to move a little bit to, I mean, to look at Reticolo. I mean, the version developed by Jean-Paul, I mean, the extension. I don't want to just to invite you, in fact, to join Jean-Paul. So just to show here all the program which have been developed during more than 20 years. Jean-Paul started a little bit before 2000 with MATLAB. You see problem for grating analysis. You see me. This is very, very nice S matrix and even generalized S matrix method that has been implemented. You can find Rhett Marcus, Rhett Abeles. Abeles is a famous name, but you have also Rhett Bono. You have many things. Rhett Carminati, which is the director of our institute, also can be found somewhere. So this is Rhett Cadillac. Cadillac was a math guy in Marseille, etc., etc. Many other problems about that. Like to say, just to show something like Rhett and this, which is not electromagnetism, but which is providing a list of dispersion refractive index for many material. I am looking at that. You see, I am just scanning. So this database is already a lot of work. This just to imagine that for, let's say, silver, okay, that you can get like this. You see you have something like in between 10 and 20 different silver, which has been encoded completely by COMSOL. So you can just ask a wavelength and in MATLAB and have this. So that's already interesting. Just want to talk about some mode computation, very, very easy. I prepare this. So this is a mode this is a planar waveguide. So it's very easy calculation, but look at that. So you have air above, this is the index. 3.5 is a layer. And then you have a substrate with a refractive index 2. And we are looking for a target effective index, which is 3 and 1.1. So we are looking for two modes. The polarization is TE. And then you can just read it like this. No, you should read in. Sorry about that. And then you get this kind of curve where you see here you have a guided mode. The effective index is purely real, like this. This is a field profile. And here you have a leaky mode, which is with an effective index of 1.4. So it's leaky in the high index region, you see here. And it is just confined in air. Finally, I would like also to, with red mode, to show you a plasmon case. So this is we fix the wavelengths. No, this is not. Sorry, this is not the good. This is not the good one. Yeah, here is a plasmon case. You see where you fix the wavelengths, the index. So you have air above. You have a film, which is probably gold or silver, I don't know, and you have a glass substrate. The thickness of the film is 0.02. The polarization is TM, and then you get this immediately where you have the effective index. And here the mode profile where you have here the confinement into the metal, and here the confinement into the substrate. And here you have the very thin layer, which is only 20 nanometer. Just another example here. If I do help more complicated structure, red mode, but it's just an example. I am just looking at red mode, and even red mode do more than that. Then I can take this here. It will be, now it's a more complicated system where you have a hollow fiber, according to the simulation I was looking this morning, where you see, I don't know, here you have probably air around here, you have a high index material here, and you have an inclusion which is square with a low index material, and you see the modes which have been calculated in that case for this system, very obviously. With that, I would like to close the sharing and to thank you for your attention.